Imagine I ask you to find the average salary of 100 employees. You can calculate the mean and get a value, let's suppose 80,000. Sounds simple, right? But what if 90 employees earn between 30,000 and 70,000 while 10 employees earn 2 lakh, 5 lakh or 10 lakh? Suddenly that 80,000 average does not tell you the complete story. This is why two powerful concepts in statistics become extremely useful: skewness and kurtosis. So by the end of this video, you will understand what they mean, how to calculate them, and most importantly, how a data analyst actually interprets them. In the last example where I told you that a class B having number of students, let's suppose 10, and average equals to 80. Does it mean all the students have average 80, 80, 80? No. If I don't get the data points, do we have any factors from where we can get to know? Yes, variance and standard deviation that we have learned, which helps us understand how far the data points are from the mean. Like in that example, the standard deviation, we assume it to be 10. So the data points lies in the range of 70 to 90. But do we actually know where most of the data points are? Is it in the range of 70 to 80 or 80 to 90? We just know that our all data points are in the range of 70 to 90, but we don't know with the help of standard deviation or variance that where these points are actually. To get that information, we need to understand the shape of the data, and that is why we got skewness. So the shape of data, it's matter in statistics, because mean and standard deviation describe center and spread, but not the complete picture. Two data sets, same mean and standard deviation, but yet they look completely different. In order to understand the shape of data, that's why we are talking about skewness and kurtosis, that will reveal the true form of the distribution. So let's begin with the skewness. Skewness tells us about the symmetry of the distribution. In simple words, it is the data balanced around the center, or does it have a long tail or one side? There are three common situations that we have. First, zero skewness. The distribution is roughly symmetric. Second situation, positive skewness. We call it as right skewness also, that we have a long right tail. And third situation, negative skewness, called as left skewness. The long tail extends towards the left side. Now let's try to understand it with the help of an example. So consider that we have some data points. Let's suppose I'll say 1, 2, 3, 4, 5. 5 points, 1 each, right? So what is the mean of this? The mean, if we calculate that, 1 plus 2 plus 3 plus 4 plus 5 divided by total number. So it will come out to be 3. And if I talk about median, right? If I talk about median in that case, so median is the data should be sorted and the middle value, if we have odd numbers, in that case median is also equal. That is 3. So in this case, when the mean is equal to median equals to mode, our distribution follows this way. Where if we are going to cut it into from the center, we'll get equal halves on both hand side. That means left side, right side, both are equal. This is what we say the distribution is equal and data points are equally distributed along the range. Symmetric. But if the data is not symmetric, let's suppose in the same data 1, 2, 3, 4, 5, I have a number 10 also, or 100 included in that also, right? Now in that case, what will be the mean? 1 plus 2 plus 3 plus 4 plus 5, 15 plus 100, 115 divided by 6, which approximately you will get 6 1 the 6, 6 9 the 54, approximately equals to 19. That is mean. But in that case, what should be the median? If you check that, so median, we have now 3 and 3, 6 values, right? Data is sorted. In case of even, the middle two values, you add it and divide with 2. That will be equal to 3.5. 4 plus 3, 7 divided by 2. Now you see in this case, we have most of the values lies at the starting and there is only one point we have at the end. So in that case, if I draw this graph, I will get this kind of graph where I have a long right tail. That means most of your data points lies at the first half at the starting and few values you have at the end. That's why we get long right tail. In that case, your mean will be greater than median. So this is what called as right skewed data, and in that skewness will be positive, value must be greater than 0. So which will help us understand the shape of the data, that your most of your data points lies in the range 1 to 5 or few data points you have in the upper range. And similarly, we have negative skewness also, where we say most of the data points are in the higher range. For example, if I have a data from 1 to 100, right? Or it can be in any range. I'm just taking it as an assumption, right? So my most of the data points are here on the higher side and few of the data points are in the lower side only. Okay, let's suppose few students got less marks. Generally in exam, if you also see that most of the students get higher marks, right? And very few students we have in the lower side. That creates the negative skewness, or we have a left skewed data. And in that case, if you find the mean, your mean will be less than median. Okay. So positive skewness we have most commonly in where we talk about salaries, right? Because most of the people have salaries around average and few of the employees in the company have higher salaries, right? That tends to make a right skewed data. And for marks, we generally have negative. It's not, it has to be happen in that way. Just an example which I'm trying to relate it with, right? So negative skewed data where we have the mean is less than the median. So skewness helps us understand this, right? And it is very important. So this is how I hope you can understand that instead of just blindly reporting the average, a data analyst first should investigate the distribution. Because for same data, for same number of data points, same average, the distribution can be different. So we need to understand the data. So the skewness helps us in understanding the shape. Now, the next thing we have how to calculate that. Yes, we can use the function in the skew function in the Excel, right? And with Python also, with the help of SciPy library, you will see we'll apply this function, right, in the future. So this is the formula that we use. We call it as Pearson's moment coefficient that we use. So based upon the value of the skewness, we'll decide, right, that what is the distribution. Now we got to know, okay, the distribution can either be symmetric, the distribution either be right skewed data, or distribution can either be left skewed data. But how I'm going to define that, whether in any of this case, what will be the peak of this data, right? Maybe this graph could look like this flatten also. Maybe it could look like this, or maybe this could also look like a sharp we have, right? So how I'm going to define this? For this we have kurtosis, right? Kurtosis is related to the shape of the tail and the tendency of a distribution to produce extreme observations. This is where beginners often get confused. They hear kurtosis means peakness. That's oversimplification. For data analysis, it is more useful to think about kurtosis in terms of tail heaviness and extreme values. So kurtosis helps us to find how heavy are the tails. High kurtosis generally means that the distribution have higher tails and a greater tendency towards extreme points or observations. Low kurtosis generally means lighter tails. And three types of kurtosis that we have: Mesokurtic, Leptokurtic, and Platykurtic. If we have normal distribution, your kurtosis will be equal to 3. Now you might be wondering that why not 0, right? So there are different softwares, right, which are there, and they report different versions of kurtosis. Some function report Pearson kurtosis where normal equals to 3. Other reports excess kurtosis when normal equals to 0. So you always check what your software is calculating, right? So kurtosis equals to 3. The first type, Mesokurtic, this represents the normal distribution where kurtosis is commonly given as 3 or excess kurtosis equals to 0. Second, we have Leptokurtic. It has heavier tails and generally greater tendency for extreme observations. And third, Platykurtic, lighter tails and fewer extreme observations compared to the normal reference. Let's understand with the help of an example, right? So let me write here. Let's suppose we have some numbers, okay? Let me use pen. Perfect. So let's say I have some numbers. A data set 1 I have, right? In which I have few numbers. Let's suppose 48. I have 49, right? Then I have number 50, 51. Then I have 52. Let me consider that, right? And 53, 54. Okay, so this is the first data set I have taken from 48, 49, 50, 51, 52, 53, 54. I'll take another data set, right, where I'll take some numbers. 45, 49. Okay, I'll take some number. 45, 49, 50, 51. I'll take 50, 51. I'll take 52. I'll take 53. And I'll take 100. Now you see, right? Okay, two of the points have changed, last one and this first one, right? Okay, you can compare these two data sets. Data set 1 is fairly centered around 50, if you can check that, right? Okay, so 1, 2, 3, 4, 5, 6, 7 values. So if I'll check around, if I'll check the median of this data, right, that will help me in knowing the center tendency of the data, right? Okay, so 1, 2, 3, 4, 5, 6. So around 51, right? Okay, so most of the data points around 50. Data set B also looks similar at first, but if you check, we have extreme value 100. The extreme observation contribute to heavier tail and can increase kurtosis. So if you are analyzing transaction amount and suddenly you see a very high kurtosis, don't just say kurtosis is high. Ask, why are extreme observations? Why are extreme observations there? Could it be a genuine value transaction? Could it be an outlier? Could it be a data entry error, or it could be a fraud, right? So if on both of this data set you calculate the kurtosis, you will get the higher kurtosis at this value, right? Because we have extreme, we have the point which is the one on the right hand side, 100. That is an extreme value that we have, which contributes to heavier tail. And if it is heavy tail, we'll have sharp peak and we will call it as leptokurtic, right? So by seeing this data, analyzing, understanding shape, distribution, right? Because where skewness helps us understanding the shape of the data, and the kurtosis that we have will help us to understand that how the tailness of this particular data that we have, right? Okay, this is why we are using, and we have to be very careful while we work with this, right? Because this will help us in giving the better judgment of the idea of the data, right, that we have. Okay, so how heavy are the tails? Kurtosis will help us understand that, right? So in this example, like we see, we have extreme point, heavy, it will contribute to heavy tails, right? That means there are more extreme outliers than normal we have a chance to have, and commonly it happens in financial returns where rare cash occurs, crashes occur, right? So this is that's it from my side for this topic, skewness and kurtosis. I hope with these examples you are able to understand and relate it to also. So follow MindXide for more such videos.